Hi, my name is Kanon, and today we'll be talking about the comparison test. First, we're going to be talking about the direct comparison test. This provides a way of deducing the convergence or divergence of an infinite series or an improper integral. All terms are going to be positive. However, if the terms are all positive after a particular term, then the direct comparison test can still be applied. And there's two possible conclusions using this comparison test. If the larger series converges, then the sum of the smaller series must also converge. And there's also the opposite of that. If the sum of the smaller series diverges, then the larger series must also diverge. Conclusive comparisons can be made between fractions with either like numerators or like denominators. We just compare these terms of an unknown series to the term of a known series, which is usually a geometric series or a p-series that we already know converges or diverges. We are going to start with this problem here, which is the summation of 1 over n to the third plus 1 from when n equals 1 to infinity. So first we must ask, what can we compare this to? Well, we can compare this to, I'm going to put that. We'll put the summation from 1 equals n to infinity of 1 over n to the third. And we know this converges because of p-series, where p is equals 3, which is greater than 1, so we know it converges. So now, before we're using the comparison test, we need to determine whether this is going to be bigger or smaller than 1 over n to the third. Or this is bigger or smaller than this. So we can set the denominators both equal to each other, or less than or equal to each other, which is the same as basically doing 1 over n to the third plus 1 is less than or equal to 1 over n to the third. Since we know that this is bigger, that means 1 over that is going to be smaller. So now we can start the comparison test. We can put it in the intervals of 1 over n to the third plus 1, which is less than or equal to 1 over n to the third, since n goes to 1 to infinity. And we know that this one is the smaller one, as we just created from up here. And this one is the bigger one and converges. And so we know since the bigger one converges, then the smaller one converges, as we just said on the last slide. So how we would write that out is because the summation of 1 equals n to infinity of 1 over n to the 3 converges by p-series test, then since 1 over n to the 3 plus 1 is less than or equal to 1 over n to the 3, then the summation is 1 equals n to infinity of 1 over n to the third plus 1 also converges by direct comparison test. And there's that one. Our next example that we're going to do is the summation of the absolute value of secant of n over n. And first we're going to do, since the absolute value of cosine of n is less than or equal to 1, and the absolute value of secant of n is greater than or equal to 1. So now that we have that, we're going to compare this to the summation of n equals 1 over infinity of n of 1. And we know that this diverges by harmonic series test. So now we can start the direct comparison test. So we can do secant of n, absolute value secant n over n is greater than or equal to 1 over n, as we determined up here, which is greater than or equal to 0. And since we know that this one is bigger, this one is smaller, and diverges, then both diverge. And how we would write that out is since the summation of 1 equals n to infinity of 1 over n diverges by harmonic series test, then since secant of n, I don't know why that just got bold, is greater than or equal to 1 over n, which is greater than or equal to 0, then the summation of absolute value of secant of n over n also diverges by direct comparison test. Next, we're going to be talking about the next comparison test, which is the limit comparison test. The limit comparison test is a method of testing for the convergence of an infinite series. Oftentimes, a given series closely resembles a geometric series or a p-series, but you cannot establish the term-by-term comparison necessary to apply the direct comparison test. So a useful test in these circumstances is the limit comparison test. We use this when term-by-term comparison is hard to prove or verify. So basically what it's saying is if the summation of a sub n and the summation of b sub n then the summation of a sub n or b sub n both converge or both diverge if they're all positive numbers. And the summation of a sub n is generally the series to be tested, and the summation of b sub n is the series that you already know that's convergent or divergent. So usually a sub n is the series that you're going to be tested or given, and then b sub n is the one that you make up. It's like the known series that either you know converges or diverges. And so the addendums to the limit comparison test is basically if the limit of n goes to infinity of a sub n over b sub n equals 0, then the summation of b sub n is convergent, and the summation of a sub n is also convergent, meaning that b of n is the bigger series. The idea of the comparison test of the biggest series, b sub n converges, so then most of the smaller one converges as well. And the second one is limit of n goes to infinity of a sub n over b sub n equals infinity, and the summation of b sub n is divergent, and then the summation of a sub n is also divergent, which is basically a sub n is the biggest series, so b sub n diverges, so is the bigger series, which is a sub n. Our first limit comparison example today is going to be the summation of 1 over 2 to the n power minus 5. So first we're going to compare this one to, we got to figure out what equation or what summation we want to compare this to, and this one looks pretty similar to the summation of 1 over 2 to the n, which also is the summation of 1/2 to the nth power. And this is a geometric series or known series with a ratio of 1/2, which is less than 1, so it converges. Now that we have that, we can do the limit comparison test. We do the limit of n to infinity, so we're going to take our series that we're given, which is 2 of n minus 5 over our known series or unknown series, 1 over 2 to the nth power, which equals to the limit of n to infinity of 2 of n over 2n minus 5. And this is an indeterminate form. And so we're going to have to use l'Hopital. We know we all love that. This is for AJ's video. Which will equal about to the limit of n goes to infinity of 2 to the n to the ln of 2 over 2 to the n of ln of 2, which that all cancels out. So it equals to the limit as n goes to infinity of 1, and 1 is bigger than 0. So since the summation of 1 over 2 to the n power converges, then by using comparison test, limit as n goes to infinity of 1 over 2 to the n minus 5 converges as well. So they both converge, since the one to be compared to converges, and since that one is the other one, then they both converge. And our last example for today will be the summation of 5n minus 3 over n squared minus 2n plus 5 from n equals 1 to infinity. So first we got to see what we want to compare this to, and since we can see that the powers here is going to be 1 over 1 power, 1 over n to the first power, and we have to do something similar, so we're going to compare to the summation from n equals 1 to infinity of 1 over n. And so now we can start our limits and comparison test. The limit as n goes to infinity of 5n minus 3, but the one that we are given over the one that we are choosing to use, over 1 over n, which equals the limit as n goes to infinity of 5n squared minus 3n over n squared minus 2n plus 5. And now this, again, is infinity over infinity, so it would be indeterminate form. So we have to use L'Hopital, LH, I'll abbreviate it this time, which will equal to the limit as n goes to infinity of 10n over 2n minus 2, which equals 5 over equals 5. So, as we can write this out, so by the limited comparison test, the summation of 5n minus 3 over n squared minus 2n plus 5 diverges. Because they act the same if a limit of L is greater than 0. They act the same, and since we know that this one diverges, then both diverge. Thank you for your time. Hope you learned something.